something called significant figures. Now, we're going to go through about 5 or 6 rules with significant figures. Tell me, first of all, did you think this is a term that's familiar to you, or not really? Are you familiar with significant? Okay, kind of not. How about, tell me, what am I having you write down here? A lot or a little?
Just the numbers.
Okay.
2, 4.
Just the numbers. Okay, gotcha. Okay. So I want to talk through the rules. So I'm going to give you a second to write down, and then I want to allow you to process while we walk through it. Okay, so write it down, and then we'll process. Let's talk about what is a significant figure and why do we use them, okay? Significant figures give us a way to figure out basically how precise our measurements are, right? It gives us a way to figure out how exact our measurements are. Are they estimates, or are they written exactly as I took my measurement? Okay, that's what significant figures kind of allow us to do in a pretty generic definition, but that's essentially what they let us do. They figure out how exact is my measurement, okay? If I look at this measurement right here, my first rule for significant figures is that any number that's not a 0 is significant. Okay? Can you take a guess as to why that might be? Do you ever add in like digits for no reason? Right? If you put an 8 in a measurement, it's probably for a good reason, right? You probably did put some thought into it. You read it or you estimated it, right?
Why would a 0 be significant?
Okay, so zeros they're kind of our point of contention because those are numbers that could appear if a number has been rounded, right? If my number is at 38 and it gets rounded up to 40, now I don't know, is it 40.0? Is it 38.5? And it's been rounded. So that's where zeros get a little bit tricky. And so that's where our point of, questions are with significant figures. All the rules have to do with zeros, okay? So there's 3 classes of zeros. I don't really need you to think about 3 classes, but there's rules that go with zeros. Okay, so the first rule that I want you to think about with zeros is called leading zeros. Okay, they come before digits start. Leading zeros come before any digits start, regardless of if they're before or after the decimal point. Okay, any 0 that comes before a digit is non-significant. It does not count when we look at significant figures. And this rule is a little bit counterintuitive, so I know I'm starting with like the hardest rule first, but this rule has to deal with these zeros being placeholders. They're placeholders. And so what I mean when I say that is, let's say that this was measured in meters, 0.048 meters. Now, if my number was this small of meters, shouldn't I have just measured with something else? Shouldn't I have just measured in centimeters? Yeah, right? If I would have measured in centimeters, I would have got 4.8 centimeters. Like, that's a much more manageable number. So when we have zeros in front of our digits, although it shows us it's a small number, it's not helping us with the exactness of our measurement. It's just showing us that it's a small number. So we should have chosen a different measurement tool. Does that kind of make sense? So zeros that come before any digit starts are non-significant. All right, something they call captive zeros are zeros between digits, and those are significant because they're just part of the number, right? 16.07, I thought about the 7 that goes on the end, so obviously the 0 had to be a part of that. So I've got all 4 significant figures in this scenario, okay? I should have gone back here. Let me go back to this last one real quick. Those zeros are non-significant, so my 2 sig figs come from those 2 right there. Okay, 16.07, my significant figures are 1, 2, 3, and 4. Okay, you'll see maybe some books or some assignments call them significant digits. That means the same thing, okay, but I will call them sig figs. So I've got 4 significant figures there. Any questions with that so far? Okay, so what if I give you a number like this? 0.04099. How many sig figs are in that measurement? 4. Good. 1, 2, 3, 4. Okay, we feel comfortable with that? All right, very good. The next one is called trailing zeros. Okay, trailing zeros. Trailing zeros are at the right end of a number. They're significant only if they have a decimal point. So I'm going to talk about that a little bit. Okay. Zeros to the right of digits after a decimal point are significant because they give us a measure of the exactness of our measurement, right? This number right here, I read those digits and I estimated that one. I think it's exactly on 0.30, right? I read those digits and I estimated that one. So I think it's exactly that. So those are all significant. 1, 2, 3, 4. Okay, all significant there. Okay, because I think those are exactly 9.30. Bless you. But when I have trailing zeros with no decimal point, this leads me to have questions. Okay, it leads me to have questions. This number right here, 150, I don't know how many digits are significant here. Right? I know I've got 2 for sure, but is this one significant or not? I don't know. I don't know how exact this measurement is. Without a decimal place, I'm unsure as to, was it 147 that got rounded? Was it 150.00 and they just left those off? Like, I don't know. And so when we run into things like this, we can't even identify how many significant figures there are. We don't even take a guess. We just say it's ambiguous. Okay, ambiguous means we're just not sure. Yeah. Ambiguous numbers are any number with a trailing zero, no decimal. Okay, so we don't take an attempt. All we do is we write ambiguous. Okay, we don't know if it's exact or if it's been rounded. So that means number just like 10, ambiguous. Right? I don't know how many. 8,000, right? Ambiguous. What about this number? Is it ambiguous? What about this number right here, 17? Is it ambiguous?
Yeah.
Nope, because it doesn't have a 0 at the end. Non-zero digits are significant. So this one, we think there's nothing that we have a question about. There's no zeros there. So sometimes we forget that we think that anything without a decimal place is ambiguous, but that's not true. Okay? So if it's got a whole number that without zeros, it still has 2 significant figures there. 1, 2. Uh-huh.
But even if it could have been right.
Exact numbers have an infinite number of significant figures. And so that's not, I don't really need you to worry about the infinite part of it, but exact numbers, you don't have to worry about significant figures. So when we say exact numbers, we think of things we use to convert. So conversion factors are exact numbers. If you have to find the average of something, like let's say you take the average of something, when you divide it, let's say you take the average of 5 numbers and you need to divide it by 5 at the end, you don't have to take that 5 into account when you're looking at significant figures because it's an exact number that you counted. Okay, it's not measured, it's counted. Okay? All that you have to take away here is that if you've got numbers that are exact, okay, that are given to you in terms of conversion factors or things that you counted, you don't have to use them in significant figures. Measurements are what we're really concerned with significant figures. Okay? All right. Okay. How comfortable are we with scientific notation? A little bit, not so much. Okay. So scientific notation, what is it used for? Okay, what do we use scientific notation for? Okay, it allows us to express really big and really small numbers in a little bit of more manageable way. Okay, if we've got a number that's 0.00000000009, right? That's not that fun for us to write out every single time. So we might write it in scientific notation. Okay, you might also hear it be called power of 10 notation. That's only because we literally put them into powers of 10. Okay. So I don't usually call it that. I'll usually just stick with scientific notation, but you might see it called power of 10. It's the same thing. All right. When we use scientific notation, we follow some sort of template. Okay. Our template, it kind of looks like this. M times 10 to the n. M times 10 to the n. That's kind of the generic template for scientific notation. And what is the rule? Do you know the rule for this number right here? What's it have to be? You remember? It has to be in the ones place. So it has to be between 1 and 10. M has to be between 1 and 10. Okay, so yes, it's got to have a ones place. Has to be between 1 and 10. What's true for the exponent up here? Can it be both positive or negative? the exponent in scientific notation could be positive or negative. Could it be like a fraction? No, right? It's a whole number that's either positive or negative. Okay?
It has to be an integer.
Has to be an integer. Okay? Anything to the zero, is zero an integer? Okay, I don't know.
I mean, it is.
Cool.
Yeah.
It could be a 0 too, but that would just mean anything to the 0 power is what?
0.
1. Anything to the 0 power is 1. That's okay. Yeah, you were really, really confident, which I love. But it's 1. Now you're not going to forget it. Okay. Anything to the 0 power is going to be end up just being 1. So it would be silly for us to use scientific notation to the 0 power. I mean, that just doesn't make sense for us to do that because it's just 1. Like if it's just 1, just write 1. Okay. So anyway, all right. Let's see. If I need to take numbers and put them into a certain number of significant figures, scientific notation is a great way for me to do that. So let's say I needed to express 300, this ambiguous number. Okay, ignore that decimal place for a second. If I had 300 and I needed to write it with 3 significant figures, I should put it in scientific notation because if I add a decimal place, that assumes that there's a 0 that follows. So I cannot just put 300 with a decimal place. I don't like that. Okay? 300 with a decimal place assumes there's a 0 that follows that. So that would be how many sig figs? 4. So that would violate my rule. If I needed 300 with 3 sig figs, the only way I can do that is to put it into scientific notation. 3.00 times 10 to the second. Okay, do you know where that exponent is coming from? Bless you. Do you know where that exponent is coming from, or do we want to walk through that real quick? Let's walk through it real quick. Okay, so if I take my original number, which is 300, and I need to put it in scientific notation, okay? I need to locate where is my original decimal place. Well, my original decimal place is right here, right? I'm not showing it, but that's where it is in 300, right? And where do I want it to be? If I want my number between 1 and 10, where I want it to be? Right there, right? So how many places did I move it? 1, 2. Now, some people like to tell you, if you move it to the left, it's positive. If you move it to the right, it's negative. I don't like that. Okay, because sometimes I count this direction and sometimes I count this direction. Depends on what I want to do that day. Okay, so I don't like to memorize it that way. What I want you to think about is when I put it in scientific notation, it's going to be 3.00 times 10. And I moved it 2 places. So I'm going to put my 2, but I decide, is that exponent positive or negative by looking at my original number. My original number was 300. Is that greater than 10 or less than 1? Greater than 10, which means my exponent needs to be positive. That's the only thing I need you to think about. If my original number is greater than 10, my exponent's positive. If my original number is less than 1, my exponent would be negative.
If it is 1, is it still positive?
So if it is 1, like 8 times 10 to the first, that would be trying to express the number 80. Is that what you mean?
I think.
Okay, so let's say, what if I wanted to put this number into scientific notation? 0.493. What if I put that number in scientific notation? It would be what? Here's my original. My decimal place needs to be there, so I'm only moving it 1 spot. So it would be 4.93 times 10 to the negative 1. Because my original number was less than 1. Okay? So I don't want you to worry about moving it left, moving it right. You just have to think about how many spots does it move, and then decide, is it going to be positive or negative based on that number that you're trying to express, right? Because that's what scientific notation is. It's an abbreviation of a real number, right? It is a real number. It's just abbreviating that number. Okay, how we feel about that?
Right.
You want to try a couple more, putting them in and out?
Yes.
Okay. Let's say I want to put this number into scientific notation with 4 significant figures. So I want it in scientific notation with 4 significant figures. In scientific notation with 4 significant figures. So that means you need to round that number to have 4 sig figs. Do you want me to do it? Do you want me to do one first? Okay, so if I want it with 4 sig figs, first of all, let's just get the scientific notation part down first. Here's my original decimal. Here's where it needs to be. Agreed?
Yeah.
So that's 1, 2, 3, 4, 5, 6, 7, 8, 9 spots. So it's going to be times 10 to the positive 9. We agree with that part so far?
Yep.
Okay, I'm going to go 1.43. That's 3 sig figs so far. My fourth sig fig would be a 6, wouldn't it?
No.
But what about this? We've got to round it up. So I'm going to go 1.437 times 10 to the 9. And that leaves me with 1, 2, 3, 4 sig figs. Yeah.
Why can't you have 5?
I just told you can only have 4. Okay. Yeah, so here's how we're going to know. Okay, we're going to, in a couple slides here, we're going to look at math rules with significant figures. So when you add and subtract, concentrating on significant figures, you've got certain rules you have to follow. And when you multiply, divide. So you're going to know in my answer, I'm only allowed to have so many. And so that's going to dictate where you round. Yep, good question. Yeah.
How do you know to move the decimal point after the 1 instead of after like the 1 and 4?
Because my number that goes right here always has to be between 1 and 10.
Oh, right.
So I'm finding out where's my ones place, right? Well, if I put my decimal here, this number is not between 1 and 10. Okay? Yeah, good question. Yeah.
So, I don't know if I missed something earlier, but like, I'm trying not to sound mean or anything, but.
The last rule for significant figures is that any visible digit in scientific notation is significant. Sorry, I didn't realize I left that off. Okay, any visible digit in scientific notation is significant. And so when I say visible digits, I mean I don't care what the expanded version of the number looks like, right? Times 10 to the 9th, I don't care about the times 10 to the 9th. I care about these digits right here that are visible. So those are all the significant ones. So 1, 2, 3, 4. So I apologize. I forgot that I left that one off. Okay, so that makes it a little bit simpler. Any visible digit in scientific notation. I don't care about the expanded number. I just care about the ones I see. Okay, so let's practice a couple more in and out of scientific notation here. Let's say that I had this number right here, 0.0003870, and I want it into scientific notation with 2 sig figs. Okay, I want you to put that number into scientific notation with 2 significant figures. And so I want you to try it here, and then we're going to walk through it together as well. Here's my original. Here's where it needs to be. How many of you accidentally took that all the way to the end? Okay, sometimes that's a common mistake. We only want to go to where the number is between 1 and 10. Okay, so my final scientific notation here is going to look like this. 3.9, because my 8 has to be rounded up. Okay, 3.9 times 10 to the negative 1, 2, 3, 4. Okay, to the negative 4, because my original number was less than 1. So I want to do one more thing to kind of check here why we do what we do, so you can kind of see. Okay. If I expanded this number out, 3.9 times 10 to the negative 4. Let me give myself some room here. 3.9 times 10 to the negative 4 would look like this, 0.00039. If I would have left this at 3.8 times 10 to the negative 4, it would have been 0.00038. Right? And so the reason we round is because which is this number closest to? 3 point. Yeah, you see it? That's why we do that. Since this is just a snapshot of a number, we lose a lot of precision when we put numbers into scientific notation. We lose a lot of exactness. So this is just a snapshot of this number we're trying to represent. This one is closer to my actual number than this one is. So that's why we do that rounding. Does that make sense? Why? I want you to know the reason behind we're doing that.
The rule of math.
So let's try the opposite direction here. Actually, let me just get a white screen here. All right. So let's say that I want you to expand. That's what the verbiage you'll hear is expand this number out of scientific notation. So if I say 4.16 times 10 to the third, expand that number and make it my actual number now. Okay, expand it out. Okay, so what that looks like is I'm going to write out 4.16 times 10 to the third. Now, my positive exponent tells me my number is going to be big or small.
Big.
Big. So I'm going to move it to make my number bigger. 1, 2, 3. I add in a 0, right? Whatever extra space I have, I add in a 0, and I'm at 4,160. Now, do we have any idea if that was the actual number that was trying to be portrayed when we put it into scientific notation? Nope. But that's as close as we can get. Okay, we don't know. If we're just given this to start, we don't know. Was it 4,157 and it was rounded up? Like, we just don't know. But that's as close as we can get. Okay?
So a scientific notation is another way of estimating?
Kind of, yeah. It gives us 198,000, and I need it into scientific notation with 2 sig figs. Okay? So I want only 2 sig figs here. Okay. This was a great question because this is one that will come up. So if I wanted to put it with 2 sig figs, you might be thinking like, oh, I'm going to do 1.9 times 10 to the 5th. But is that true? No, because 1.9 times 10 to the 5th would be 190,000, right? Not a super great representation of what my number is. So instead of being 1.9, this makes this round up to now become 2.0 times 10 to the 5th. Because that represents the number 200,000. And this number is much closer to my actual than this one is.
And that 0 after the decimal would be a significant figure?
Yep.
Okay.
Yep.
I think I'm starting to get it.
Okay. Very good. Does that make sense? I make sure I counted right. 5, 1, 2, 3, 4, 5. Okay, yeah, we're good. How many of you had that? Did you get that? Okay, a few of us. That's a tricky one. Okay, it causes us to round that up so that the snapshot we're giving is as close to our real number as possible. Okay. Is it for multiplication and division? Maybe highlight that in your notes, because there's different rules for multiplication, division, and a different set of rules for addition and subtraction. Okay, so they're very different rules, and sometimes it's easy to get them mixed up. So these are for multiplication and division. The number of significant figures in the result is the same as the least precise measurement in the calculation. Okay, so I want maybe you to write this on the side. You're going to say we're going to round our answer to the fewest number of sig figs. Okay, we're going to round our answer to the fewest number of sig figs. So both of these are saying the same thing. This one in a little bit more human language. This one in a more scientific. Okay. Round our answer to the fewest number of significant figures that we used. So I'm always going to encourage you to just do the math and then do your rounding. Okay, do the math, then do your rounding. So let's take a look at the math that goes with this one. Okay, do you guys have your calculators out? Why don't you go ahead and grab them out if you don't have them out quite yet. So I'm going to take 1.342 times 5.5, and I'm just going to write out my raw answer. What's my answer before I do any rounding? 7.381. Agreed? Right, just with the math. Now we're going to look at our two starting amounts. Okay, my first starting amount is 1.342. How many sig figs do I have in that number? I have 4. In my second number, I only have 2 significant figures. So my least precise value only has 2 sig figs, which means my answer is only allowed to have 2 sig figs. So that's when I was talking about earlier, you're only allowed to have so many. This is why, okay? So my answer is only allowed to have 2 significant figures. Can I round that to a place where I only have 2 significant figures? Yeah. Can I just go 7.4? And that's it, right? Do I need to put that one in scientific notation? No, I don't need to put it. I could go 7.4 times 10 to the 0, but like, why? You know, I don't need to. Right? 10 to the 0 power would be 1, so 7.4 times 1 would be 7.4. I don't need to do that. Yeah.
Can you add zeros to the end of the 5.5 to make it?
Nope, because we didn't take this measurement. Okay, and if we did, we can't estimate 2 digits, right? We're assuming that this 5 is estimated. So we can't estimate any more on that. Yeah, good question. We don't adjust our initial measurements. Okay, so 7.4, that's it.
This is only for multiplication.
Multiplication and division. Yeah, let's try another one. Let's do another example. I don't have one on your sheet, but let's just write out some other examples. Let's say I wanted to do 462.3 divided by 12.9. 12.90. Okay? So we're going to do the math just like normal. 462.3 divided by 12.90. I get 35.8372, blah, 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 blah. I keep going. I'm not going to write them all out. Okay? But my number, it does keep going, but it doesn't matter. I'm not going to round past that point. Okay? How many significant figures am I allowed to have in my answer here? 4, because both of my starting amounts have 4 sig figs. 1, 2, 3, 4, and 1, 2, 3, 4. Okay, both of them happen to have 4, so I'm allowed to have 4 in my final answer. So where should I round this to get to 4 sig figs? 35 point what? 84. Very good. Okay. Let's try one other example. Okay, one other example here. Any questions so far? Are we hanging in there? Yeah. We don't have to because we're allowed 4. I'm going to show you one here that's going to make you do it in scientific notation. Okay, but since we have enough, we're allowed 4 significant figures here. I don't need to. Okay. Let's try one here. Let's try 17.91 times 9.6. And we're going to put our answer in the correct number of significant figures. All right. Without doing any rounding, I got 179.936. But how many sig figs am I allowed here? Only 2. So do you see a problem? Can we just do this? 17? No. Okay, no. Because that's not even close to the number we're trying to represent. So what do you think the solution is going to have to be? I'm going to have to put it in scientific notation. So I'm going to have to go 1.7 times 10 to the what?
Second or negative? Second.
Yep. Times 10 to the positive 2 because my number is greater than 10. The number I'm trying to represent is greater than 10. And so why did I not round that to 1.8? Yeah, it's a 1 right there. And 170 is closer to this number than 180 is. Okay, so 1.7 times 10 to the second. Does that make sense when we have to put it in scientific notation? Some things that will require us to do that. All right, we're going to get through our last little math operations thing here, and then I want to be done for today. Sorry, I don't usually go the whole hour, but now this is for addition and subtraction. So this is a different set of rules, addition or subtraction. For addition and subtraction, the result has the same number of decimal places. Okay, this is totally different. Decimal places than the least precise measurement in the calculation. Okay, so with multiplication and division, we were concerned with significant figures. And now with addition and subtraction, we're concerned with decimal places. Okay, it's really tricky and kind of a difficult thing to remember because when we talk about sig figs, we want to count sig figs, but this one is decimal places. So highlight that one if you really want to. That's an important one. Okay, addition and subtraction. So if I do the math here, I actually already did the math for you. So 23.445 plus 7.83 gives me 31.275. But I'm not looking at sig figs, I'm looking at the number of decimal places. That tells me how precise my value is. So this one has 3 decimal places, this one only has 2. So how many decimal places am I going to be allowed in my answer?
2.
Only 2. So I need to figure out how to round this to 2 decimal places. So 31.28. Okay? 31.28. How do we feel about that? Okay. All right, let's try another practice here. 4.9 plus 6 plus 8.2. Let's add those ones up. So when I did my math, I got 19.1. Can I keep it there? Why not?
There's no decimal place.
6 does not have a decimal place. It's rounded to a whole number, which means my answer has to be rounded to a whole number, which means it's going to be 19. That's tough. Now, I'm going to give you one that's similar to that, okay, but it's going to require a little bit of something else. So let's say we add up 4.9 plus 6 plus 8.8. So that gives me 19.8 as my raw answer. Okay, so now what do I have to do?
19.7 is right.
Is it 19.7?
Yeah, because 9 plus 6.
Oh, I'm sorry. You're right. Oops. 19.7. Okay, still going to work the same. 19.7. Can I have a decimal place on there? No. So what do I round it to?
The nearest.
20. So do I just leave my answer like that? What's wrong with that one? It's ambiguous. It's ambiguous, and you can't give ambiguous answers. So what do we have to do now? Can I add a decimal place like this? Nope. So that doesn't work. So how do I fix it? Scientific notation. Scientific notation without any decimal places. Scientific notation, and I can't have any decimal places because that's my rule. So my scientific notation has to be 2 times 10 to the first. Whew.
Baby.
Crazy, huh? Pretty wild.
Yeah.
Yep. You like it? Okay, not too bad. Not too bad.